this video, we are going to discuss the definitions of precision and accuracy. I will show you examples of the difference between precision and accuracy. We'll talk about taking measurements on a ruler and how you must add an estimated digit to the end of every measurement. And then we'll also discuss significant figures, or as I typically call them, Sig Figs. What exactly are significant figures and how can you calculate the number of Sig Figs in a measurement? Okay, let's get started. Definition of precision. Precision refers to how close together a series of measurements are to each other. So that means that if you have several measurements and they are all very similar to each other, then that set of measurements is precise. Accuracy refers to how close a measured value is to an accepted value. That means that when the measurement agrees with the correct answer or the accepted value, then that particular measurement is accurate. So here are some examples. If a dartboard represents a target and the bullseye would be an accurate measurement, that dart, as well as these next three, did not hit the bullseye, so these are not accurate, and because they are so spread out, they're not close together, these measurements are not precise. So not accurate and not precise. Now we consider that these darts, while they are not accurate because they're not hitting the bullseye, they are close to each other. These measurements agree with each other. So they are precise because they are close to each other, but again, they are not accurate because they did not hit the bullseye. And finally, in this scenario, the darts are close together and they are on target. They are on the bullseye, so they are both precise and accurate. Well, now that you understand the difference between precision and accuracy, let's see an example with some numbers. A woman gets on the scale and she wants to decide if the scale is an accurate scale. So she decides to weigh herself on different scales, and her actual weight is 110 pounds. So on the first scale, as you can see from these four measurements, these numbers are not close together, and they are not, except for maybe 107 is sort of close, they are not close to her true weight, which is 110 pounds. So like the first dartboard, these measurements are not precise and they are not accurate. If another scale gives her the following results when she steps on that same scale 4 times, while yes, these numbers are close together, 149 and 150, her true weight is 110. So this particular scale is precise because of the consistent, reproducible results that she's getting, but it's not accurate. This scale is off by 40 pounds, basically. Finally, if this scale gives her consistent readings that are close together, 109, 110, it's both precise and accurate because the numbers are close together and they are correct. Okay, now we're going to talk about measuring objects on a ruler. As you can see, and this is a centimeter ruler. It's not labeled as centimeters, but that's what it is. This pencil is longer than 6 centimeters. So we're not able to say it's 7 centimeters. It's definitely 6 point something. And that's where the estimated digit comes in. So I, for example, might call this 6.1 centimeters. And as you can see, the 1 is the final digit, and that is considered to be the estimated digit. Now suppose that we're measuring an object where it falls on the line. We still are unable to call this 6. We have to say more than that, 6 point something. In this case, because it's exactly on the line, then you would record this as 6.0. And the 0 is at the end of the number, and it is the estimated digit. Because it is on the line, you add a 0 at the end. Here we have a ruler that doesn't seem to have very many lines on it at all. But it illustrates a point that I would like to make about how you add an estimated digit. In this case, to record the length of the pencil based on the lines of the ruler, we know it's going to be somewhere between 0 and 10. And that's all we know. Maybe it's 6 centimeters, maybe it's 7 centimeters. Could we say 6.5 centimeters? And the answer is no. every line on this particular ruler is worth 10 centimeters. So you would estimate to the ones place. You estimate 1 power of 10 smaller than what the lines are worth. So in this case, we could say 6, we could say 7, but that's all we could do. Now suppose we have a ruler in which every line that's printed on the ruler is worth 1 centimeter. We can estimate to the 10th place. So perhaps you might call this 6.7, or perhaps you might call this 6.8. Could we say that this ruler gives us a measurement of 6.75? And again, the answer is no, because every line is worth 1 centimeter, so we can only put the estimated digit 1 power of 10 smaller than what these lines are worth. So 6.7, 6.8, but we could not go out to the 100th place. We just don't have that level of precision with this ruler. And now finally, let's go to an even more precise ruler and measure the same object. So, as you can tell, this ruler has every line is worth 0.1 centimeters. I'm going to give you a close-up of expanding what that looks like. So, we are now at a point where we can measure somewhere between 6.7 and 6.8. So let's say we think it's roughly about halfway between 6.7 and 6.8. You might say that the measurement is 6.75 or perhaps 6.76, but the final digit, whatever that number is the estimated digit. And because every line was worth 0.1 centimeters, the estimated digit was 1 power of 10 smaller than that particular measurement. So we go out to the 100th place. Okay, now let's consider some examples where the length of the object, in some cases, is exactly on the line. Remember, we mentioned that we're going to have to add a 0. If the first measurement is just 6, and we cannot say anything more than that because we are only going to the ones place. But now, with this measurement, we are able to go to the 10th place. And let's take a moment to think about what that means. I'm saying that 6.0 is a more precise measurement than just 6. It's a different ruler, and therefore it does require a different level of precision. So, can you guess from this third ruler, if we're going now out to the 100th place with our final digit, this particular pencil on this ruler would be measured as, hopefully you said, 6.00 centimeters. Okay, so that is the most precise of the three measurements. I'm not changing the value. It's still considered 6 on a calculator, but in a science class, 6.00 is a different number than 6.0 or just 6. And that leads us to our next discussion, which is we'll be talking about significant figures. Okay, so we're going to talk about significant figures now, or sig figs. In a measurement, the number of sig figs include all of the known digits plus one estimated digit. So in this example, the measurement is 6.7. The known digit is a 6. Because we estimated that final digit as a 7, that counts as well. It's all significant, so this number would have two significant figures, or 2 sig figs for short. In this example, you can see that we now have a more precise ruler. Take a look at where the final estimated digit should be. Are we going to estimate to the 10th place, or are we going to estimate to the 100th place? Hopefully, you can see that because every line that's printed on this ruler is worth 1/10 of a centimeter, then we will estimate to the 100th place. So therefore, because it's exactly on the line, it would not just be 6.7, we get to add a 0. So 6.70 centimeters. Pay special attention to the fact that I had just shown you 6.7 on the previous slide, and now I am showing you 6.70. So in this chemistry class, 6.70 is more precise. How many significant figures is a measurement of 6.70? 3. So this measurement has 3 significant figures. Not 2, it has 3 because we do count that final estimated digit. And now I have to teach you some rules for determining the number of sig figs in any measurement. Sig Fig rule number 1. All non-zero numbers are significant. So what does that mean? It means any number from 1 through 9 is going to be significant all the time. So here I have a measurement, 72.3 grams. There are no zeros, everything counts. This measurement has 3 sig figs. Okay, our next Sig Fig rule. Sig Fig rule number 2. Captive zeros are significant. So what does that mean? What are captive zeros? A captive zero is a zero that is trapped in between non-zero digits. Here's an example. 800.4 centimeters. The 8, we know that counts. The 4, we know that counts. And those two zeros are captive. They are in between. So everything counts in this measurement. This measurement, 800.4, has 4 significant figures. Okay, on to Sig Fig rule number 3. If a number has a decimal point, then the trailing zeros, the zeros at the end of the number, are significant. So here is a number, 1.00. It's a measurement, 1.00 seconds. It has a decimal point. The zeros at the end are significant, so therefore a measurement of 1.00 seconds has 3 sig figs. Okay, moving on to Sig Fig rule number 4. If a number has no decimal point, then the trailing zeros, which are at the end of the number, do not count. They are not significant. So notice the measurement, 1,500 liters. There is not an exact point. There's no decimal at the end of a number. So we have 1,500 or 1,500, but these two zeros are now no longer significant. A measurement of 1,500 liters has 2 sig figs. Okay, and our final rule, Sig Fig rule number 5. Leading zeros, which are the zeros that occur at the beginning of a number. Typically this would mean you have a number that is less than 1. So leading zeros at the beginning of a number are not significant. So we have a number that would be 0.0075. This measurement has 3 leading zeros. But according to Sig Fig rule number 5, these are not supposed to count. So therefore a measurement of 0.0075 meters has 2 sig figs. Okay, so now the last thing I would like to show you, if you are confused about all of those rules that you just saw, and remember, you are welcome to replay this video as many times as you like, and you can pause the video to take notes. I'm going to give you a little rule, a mnemonic device, for remembering the number of sig figs in a measurement. And I call it the Atlantic and Pacific rule. So clearly you can see there is a Atlantic on the right and a Pacific on the left. So here's the first application of the Atlantic and Pacific rule. A number is given to you, and we'll assume that's a measurement, even though there's no unit. Let's just pretend that there's a unit. 50,200 something. That could be seconds, meters, grams. It doesn't matter. I'm focusing on the number. If a decimal is absent, so A for absent, A for Atlantic, you will start counting from the Atlantic side of the number, that is, from the right. Skip over any zeros that you encounter on that side. So I'm going to just cross them out. And begin with the first non-zero digit. So the first number I come to that's not a 0 happens to be a 2. Then continue counting every single digit, no matter what it is, 0 through 9. Every single digit is now considered significant all the way until you get to the end of the number. This measurement of 50,200 has 3 sig figs, and this is according to the Atlantic rule. You use the Atlantic rule when a decimal is absent. Let's go ahead and practice examples of the Atlantic rule. So you'll have to forgive me for not showing you units. All we have are numbers. We have to assume that these were all measurements. 200, it could be grams or meters. That doesn't matter. I'm just kind of focusing on the number right now. Every single one of these 6 numbers is going to obey the Atlantic rule because in every single number a decimal is absent. So A for absent, A for Atlantic. If we count from the right side of the number, and I'm going to go ahead and just skip over any of the zeros that are on that particular side of the number, whatever we have left from that point forward, from the end of the number, is going to be the number of sig figs. So 200 has 1 sig fig. 3,500 has 2 sig figs. 700,000 has only 1 sig fig. Now in the next example, it's 20,001. There must be a reason for 20,001 because it would be counted to the ones place for whatever reason. The first number we come to on the Atlantic Ocean side is a 1. So therefore, since a 1 is significant, everything else counts. You may remember that that's the Sig Fig rule number 2. Captive zeros are significant. Then we come to a number which is really large, 6,200,000. If we skip over all of the trailing zeros because the decimal is absent, we get only 2 sig figs. And then finally 801,300. The decimal is absent, Atlantic Ocean side. Once we get to the 3, everything counts. So this number has a total of 4 sig figs. So if the Atlantic rule applies when a decimal is absent, we apply the Pacific rule when a decimal is present. Now we start counting from the Pacific Ocean, or the right side, the left side of the number. So we count from the Pacific Ocean side, or the left side of the number. Skip over any zeros as we did before, and once you come to a non-zero digit, then you count every single digit all the way until you get to the end of the number. So this particular measurement of 0.00250 contains 3 sig figs, according to the Pacific rule. And now it's time to practice the Pacific rule. So all 6 of these measurements contain a decimal point. We'll start counting from the Pacific Ocean, or the left side of the number. 200 with a decimal point at the end implies that you have confidence out to the ones place. That measurement has 3 sig figs. 200.0, again, because you're counting from the Pacific Ocean side, the first number you come to is a 2. And from that point forward, everything counts. So 4 sig figs for that measurement. Similarly, 3 is the first number we come to on the Pacific Ocean side, so everything counts. 4 sig figs. But now, what do we do with this next measurement? 0.007. We have to skip over the leading zeros, and this measurement only has 1 sig fig. Our next example is 0.0020. Once we get to the 2, everything counts from that point forward. That measurement has 2 sig figs. And then finally, the first number we come to on the Pacific Ocean side is a 1. So therefore it doesn't matter. Everything counts from that point forward. That measurement, 1.0020, contains 5 significant figures. Okay, so now it's time to summarize what you learned in this video. First, I talked about the definitions of precision and accuracy. We said that precision applies when a set of measurements are very close together, very similar to each other. We said that accuracy is when a measurement is correct or very close to an accepted value. When you take a measurement on a ruler, you always must add an estimated digit at the end of the number, which represents 1 power of 10 smaller than what those lines are worth on the ruler. And in some cases, when a measurement happens to fall exactly on the line, then you would add a 0 in the appropriate place as far as the decimal is concerned. Finally, we talked about significant figures, or sig figs, and we said that there were several rules for figuring out how many sig figs there are in a measurement. And I taught you the Atlantic and the Pacific rule to help you keep track of when the zeros count and when they don't. So you may watch this video over and over to help you understand it, and you may see me if you have specific questions.